Hello, my project is entitled Modeling Artificial Thickening of Transonic Boundary Layers with a Pressure Gradient, and I am in Electrical Mechanical Engineering 5. So I started this project as a student of the governor's school because we all have to do a mentorship project our senior year. However, and that's how I got the opportunity to work with Dr. Gregory Jones at NASA. However, once I got there, I had a little bit of liberty in choosing my project, and I went to boundary layers because I thought it was something that was both very interesting and new to me, as well as practical and applicable in the next couple years in aerodynamics and on actual commercial aircrafts. Okay. So I looked at boundary layers, and a boundary layer is the area between the surface of an aircraft if a fluid is flowing on it and the free stream velocity. So as you can see here on this model, that would be the area between the surface and the free stream, and that would be a total area of lower momentum air because it is slower air. So how would you use that? Well, if you had an engine at the back of this aircraft, for example, then you could ingest it with this lower momentum air. That's something called boundary layer ingestion, and that would make the engine as a whole more efficient. And that is something called the tail cone thruster effort that has been proposed at NASA recently, and it would look something like this. So the first thing to understand when looking at a tail cone thruster, even the possibility of it, is how boundary layers develop and grow. So you would do that with a shortened model like this, and we put different manipulators on it in order to see how we could artificially thicken it, the boundary layer, in order to see how it would grow. And we ultimately ended up finding that our artificial manipulators made the boundary layer grow similar to actual boundary layer natural growth. So we did this with a model that looked exactly like this. This is the exact same size as the model used. It is a semi-span model, and it had 3 rakes at 3 different locations as shown here that all measured pressure, and that's how we got the data for the experiment. Now, we go here. So I looked at 3 different configurations, a baseline, 1 ramp, and then pins. So baseline configuration 7, configuration 11. And as you can see from this graph here, I plotted the boundary layer profiles. So the velocity over the free stream velocity as on the bottom axis, and then on the side, we have the boundary layer height in inches. So as you can see, here is 1. That means that it's met the free stream velocity. So as you can see, obviously baseline configuration has the lowest boundary layer, and the ramps and the pins have higher ones, as would be expected. I ran 3 different left-tailed pair t-tests, and I found that both ramps and pins were more effective, statistically significant, in order to increase the boundary layer. And between the ramps and the pins were more effective than the ramps. However, since the pins were much larger than the ramp, that would indicate that a ramp would actually be more effective, since a much smaller ramp than pins brought similar results. I also looked at a top versus a bottom view, since we tested 2 different views. One was the top, and then one was the bottom, and the bottom has a steeper pressure gradient. And so what that causes is a much larger boundary layer height because of the steeper pressure gradient, and as the pressure gradient increases, the boundary layer almost separates. So that's one of the problems that we possibly face there. I also looked at Reynolds number, which is a scaling measurement, and it compares the inertial forces to the viscous forces. And as you can see here, it is very useful in scaling, and this relationship here would imply that the boundary layer height delta is inversely proportional to the Reynolds number. And so I looked at the baseline, again, the configuration 11 pins and configuration 7, and in all 3 graphs you can see the same relationship here. Lastly, so there are some limitations in the fact that the rakes were maybe not tall enough to capture all of the boundary layers, such as the bottom, as I already mentioned, and also the types of manipulators used, because we did use 15, which is a lot. However, we only use ramps and pins. However, at a 99% confidence level, there would be sufficient evidence to conclude, as I already stated, that both the collar and the collar of ramps and pins would both simulate natural growth of a boundary layer. Now, the novelty in this experiment lies in the fact that there were 2 different pressure gradients and 15 different manipulators used, versus the only other similar tests done with a flat plate and only 1 type of manipulator. And future tests of this would include computational fluid dynamics, side-by-side comparisons to see how well that holds up to the experimental results, as well as further tests of an actual tail cone thruster in a wind tunnel.